Percent yield problems are an application of stoichiometry problems. For your percent yield problems, you're going to need to do a normal gram-to-gram problem or a limiting reactant problem in order to plug into this equation right here. Normally I just say it's A over T, but your A is your actual. That means that that is the actual amount that you recovered or produced in the lab. Your theoretical for your T is actually, according to the math, in a perfect world, if you do everything 100% correct, how much should you make in the lab? So both of these have to do with products. When you take your actual divided by your theoretical, it is a percentage, so you're going to multiply by 100 in order to get your final answer for your percent yield. And percent is actually your unit as well. There's no grams or anything with your units. So I'm going to do two sample problems. One is just a regular limiting percent yield problem. The other one that I'm going to do is actually a limiting reactant problem, and then you'll have to actually plug it into your actual over theoretical from there. So that one is kind of a three-step problem to do, where the other ones are just two steps. So I've already balanced my equation. We have sodium reacting with oxygen. We're making the Na2O2. And now it says to determine the percent yield for the reaction if we have 3.74 grams of sodium, which is a reactant, and excess oxygen. Excess just means that we have so much we'll never run out, so that is not our limiting reactant. If 5.34 grams of Na2O2 is recovered, this amount right here is my actual. That is what was actually made in the lab. I need to figure out my theoretical. So to figure out my theoretical, I'm going to take this number right here, which is a reactant, 3.74 grams of sodium. And I want to know, if I have 3.74 grams of sodium, how much product should I make? So I'm going to first take my grams and turn it into moles. Molar mass of sodium, 22.99. That is the mass of 1 mole. The second step is my mole to mole ratio. For every 2 moles of sodium, I have 1 mole Na2O2. Now in my last step, I need to take my moles and turn it back into grams. So 1 mole of Na2O2, I need to find the molar mass of this one. So 22.99 times 2 plus my 2 oxygen, that's 32, 77.98 grams Na2O2. So I'm going to take my 3.74 times 77.98 divided by 22.99 times 2, so you get 6.34 with sig figs grams of the Na2O2. So what this means is, in a perfect world that you do everything in the lab 100% correct, you don't lose any of your sample, you don't break your beaker, you have everything totally dry, whatever might happen, this is how much you should make. This is how much they did make. So we're going to take our actual, 5.34, over our theoretical, 6.34, times 100. 5.34 divided by 6.34 times 100. This has 3 sig figs, 3 sig figs. This part is a conversion factor, so you don't actually use your times 100, so you get 84.2%. So the percent yield of this problem is the 84.2%. Now on the second problem that we're going to do, this one you're going to see 3 numbers. You have 6.92 grams of potassium and 4.28 grams of oxygen. It says 7.36 grams of the K2O is produced. That number right here, that's my actual. So that's how much they actually made in the lab. This number and that number are both reactants. So we want to know with each one, with my potassium, how many grams of product can I make? With my oxygen, how many grams of product can I make? So I need to do a limiting reactant. So for this problem, I'm going to rewrite the problem down here, because I'm going to need my balanced reaction. I have, in my first problem, 6.92 grams of my potassium. And in my second problem, I have 4.28 grams of oxygen. I want to know in both cases how many grams of product should I be able to make. So the first step, we need to take our grams and turn it into moles. So we're going to take 39.10 grams. That's the mass of 1 mole of potassium. Then my mole to mole ratio, for every 4 moles of potassium, I have 2 moles of the potassium oxide. Last step, I'm going to take my moles, turn it back into grams. So I need to find the molar mass of this guy right here. 39.1 times 2 plus 16. My molar mass of the potassium oxide is 94.20 grams. So I'm going to sit tight on that for just a minute, and I'll run the math in just a second. But first I want to take my grams of oxygen and figure out how many grams of product I can make. So 32 grams of oxygen is the mass of 1 mole of oxygen. Then 1 mole of oxygen will produce 2 moles of the potassium oxide. 1 mole of potassium oxide has a molar mass of 94.20 grams. So now I need 2 different answers. The top one, I take my 6.92 times 2 times 94.20 divided by 39.1 times 4. 3 sig figs, you get 8.34 grams for that one. I'm going to do the same thing on the bottom one, 4.28 times 2 times 94.20 divided by 32. You can make 25.2 grams of the potassium oxide here. So that means that the maximum amount of product that I can make is 8.34 grams. I can make up to 25 grams down here, but I'm going to run out of potassium before I get to that point. So my limiting reactant is potassium. This right here is the maximum amount that I can make. That is my theoretical. That number goes on the bottom. On the top, in the question, it said that we had 7.36 grams. So I take 7.36 divided by 8.34 times 100, and you get 88.2% yield. So the closer that you are to a 100% yield, the better. These could go over 100% or under 100%, depending on whether they recover more or less of the product. So right here, both of these are actually pretty good percent yields.